And did you need any internet access during the talk? Okay. So it should be very straightforward.
Yeah, I think so.
We're going to be recording the talks, just so you know that. And then, do you need a laser pointer or anything like that?
I have one.
Okay, sounds good. So we'll just hook you up to the system, make sure your slides come up, and it should be all right. And then if you need power, just to make sure that the laptop stays fully juiced up, we could get into that one. Just be careful because it's not a whole lot of space here.
I think we'll be okay. And just replace the battery.
Oh, good. All right, so if you have an HDMI, we'll use that. We also have cables to hook up if you have a newer Mac.
Let me try the HDMI.
Okay.
Where's all this stuff?
Good. That's a good sign. That's me. Once I leave with this laptop, I won't have anymore. Hey, Corey?
Somebody's logged in on the laptop.
Yeah, I'm leaving now. Thanks. Do you have any audio or video?
Nope.
Okay, so I think we're ready to go. The only thing I can ask is if you try to stay within the range of podium. If you walk off screen, then obviously people will hear you.
Is this okay?
Yeah,
Pointed
that's
stuff?
the limit.
Okay.
There. Okay.
Let me see. Oh, let me just see if my pointer works. Okay.
Good morning.
Good morning.
All good?
How are you?
You were so prepared in your talk. You're like, I'll solve a problem and then type it up. And,
Oh, that was
Right. And this method seems like it would be at least amenable, like you could write complexes all the moments.
And it also would be.
Yeah. Right. Yeah.
Because what I wrote, I'm not sure that was sort of the limit of my 4-year knowledge. But I was surprised. Have you heard of this? Like, on camera symbol?
I know I ran into it like once, but I didn't like
Have
read
you
about it.
never-
And this combinatorial thing, I was like, that makes sense. Oh, that symbol, I was just like, oh, that seems like a really interesting.
Yeah, I never heard of it before. I just looked up.
I think that's really cool.
Anyway, any deficiencies in my talk, I'll blame on
Yeah.
echo noise. That's good.
Yeah.
So S should depend on X.
Well,
But then you don't have. Then the formula for the mutual information is like the average. of
right,
the-
instead of like the log of S, it's like the average of the log of S.
Yeah.
Which, from like a estimating mutual information point of view, is like still super easy. So it was like good to have that extra
I
flexibility
see, but
and still
sometimes
have it.
you might want to inject a lot more noise
Right.
than other times, depending on the signal. That's the idea. Like you
Right.
don't want heteroshomo
Right.
stochastic noise.
Right. And it seems to be important, like, because when we did it without depending on X, we couldn't beat the regular VAE, but then afterwards we could.
Oh, really?
Yeah. So it was a pretty big gap in representational capacity, or at least elbow tightening or whatever. So-
Yeah.
Okay.
About
so
15.
Mind if I introduce you and we get started?
Yeah.
Hey, good morning, everybody. Thanks for coming. I'm really happy to have Artemy Kolchinsky visiting us and giving a talk today. I met him a long time ago at a complex systems conference, and he had like all sorts of interests that were like very overlapping with mine. I think it was PhD was at Indiana Bloomington, where lots of our friends and colleagues and collaborators were. And now he's a postdoc at the Santa Fe Institute. And I mean, he does so much interesting work. So like the stuff we've talked about just during his visit is the thermodynamic cost of computation, where he's done some really cool stuff. There's this whole subfield of people who study information decomposition, like different ways of describing information among multiple parties, and he's done some like really cool new work on that. And then there's also, on top of all that, a totally another field which we're going to hear about now, which is information bottleneck, which has been really showing up a lot in machine learning and deep learning, and Artemy also has some really cool work about that. So I'll let him take it from here.
Thank you, Greg. Thanks for coming. Thanks for having me. How many of you have heard of the information bottleneck? Almost everybody. Okay. Great. That's good. So today I'll be talking about information bottleneck and some of its connections to machine learning. And I'll begin by presenting or introducing the idea of information bottleneck. And then I'll talk about how we might solve the information bottleneck problem, which I'll define using neural network techniques. And I'll finish by talking about some connections between information bottleneck and deep learning, or neural network learning, which has recently been attracting quite a bit of attention. I'm going to assume kind of a pretty basic familiarity with information theory and neural networks. Nothing too fancy. Okay, so what is the information bottleneck? By the way, please feel free to interrupt and ask questions. I definitely prefer that rather than missing something. Information bottleneck is a kind of compression technique that was proposed, I believe, in 1999 by Naftali Tishby and Bill Bialik and somebody named Pereira. And I think it's easiest to explain with an example. Actually, an example I'm going to use is weather prediction. So let's imagine that we have some kind of weather station, which maybe is in a really remote location, like this is Antarctica, and it collects some meteorological data. And we want to use that data to make a prediction about the weather tomorrow. We don't make this prediction at the weather station. We might make it somewhere else, for example, at a remote data center. So we'll need to transmit our recordings from the weather station to the data center, crunch some numbers, and then make a prediction about the weather tomorrow. And mathematically, we can represent this as 3 random variables. I'm going to use this notation throughout. So x is going to be what we call sometimes the input. So that's basically the data we have. And y, which I'll call the output or the target, is the thing that we wish to predict. And t, which here would be like the representation at the data center in this example, I'll call the intermediate representation. So t is some kind of stochastic function of x, which will hopefully capture information about y that we can use to predict y. And it's very important, these dashes here refer to conditional independence relationships, so these form a Markov chain. And this is saying that t is conditionally independent of y given x. So that means that anything that t knows about y, or any information that we can extract from t about y, also has to be in x. And now we're going to think about 2 different goals that we might have for finding a good intermediate representation t. Which again, in this case, might be like what we transmit from the weather station to the data center. So we might want to first optimize compression, which means that we want to have a small mutual information between x and t. And in this example, we might have a very low bandwidth or costly data link between the weather station and the data center, and so we want to send as few bits as possible from one to the other. At the same time, we want to make good predictions about the weather or about y in general. And so we formalize that by saying that we want to maximize the mutual information between y and t. And these 2 goals, minimizing one mutual information, maximizing the other mutual information, are actually in conflict with each other. So we get a very interesting trade-off as we favor one or favor the other. You know, in the extreme case, we can collect, for example, not compress at all. So t would be equal to x, in which case we would have maximal prediction, so the best possible prediction, but we would have no compression. We might have to use many, many bits in transmitting x to t. Or in the other extreme, you know, t could just be like a constant, like it could always be 0, so it has 0 information about x, and it takes 0 bits to transmit, but it would, of course, give us like really bad prediction, right, of y. Okay, so this trade-off between optimization, compression, and prediction, we're going to write in terms of this constrained optimization problem, and which says maximize the mutual information between y and t, subject to some rate constraints on the mutual information between x and t. And for those of you who are familiar with rate distortion theory, this is very closely related to rate distortion. I'm not going to go into that for time reasons unless you want me to, maybe at the end of the talk and I have some time. And this constrained optimization problem gives us basically a function of solutions for different values of r, so for the rate constraint. And it's quite a difficult problem to solve because of the nonlinear constraints and so on. And oftentimes what people look at is instead what's called the IB Lagrangian. So this is the Lagrangian relaxation, basically that constrained optimization problem, where instead of a hard constraint, we now optimize the sum of the prediction quality minus the compression cost, and the compression is weighed by this parameter beta, which just determines the trade-off. So how many bits of compression are we willing to trade for a bit of prediction? Now, the solutions to these form what's called an IB curve. And this is most simply illustrated on something called the information plane. This is a tool that's used very often in information bottleneck to understand what's going on. So this information plane has two axes. On the x-axis is the compression values, and the y-axis is the prediction values. And each point in this plane corresponds to one particular choice of t. Maybe, or many, each point could represent many t, but different t's fall on different points in this plane. And there's this region which is accessible, which is possible to achieve, which I here show in gray, and it lies below the information bottleneck curve, which I show in blue. And, by definition, that's the maximum possible, the information bottleneck curve is the maximum possible prediction given each level of compression, so we have to be on one side of it.
Last question.
Of course.
Is it on purpose follow a log-like curve?
This is for schematic purposes, and that's a good question because we'll see actually sometimes it looks very different. It is concave. It's known to be concave, yes.
Okay, that was what I was about to ask. I didn't know if it was necessarily monotonic or...
It's definitely monotonic because you can see as we go to the right, so we're loosening our constraint, right? But beyond just being monotonic, it is concave, but it's not actually strictly concave, as we'll see. And that's actually going to play an important role. Okay, and then, as I mentioned, basically different points on this blue line are basically different optimal solutions, what I'm going to call IB optimal solutions, that give us a different balance of prediction and compression. Okay, so how do we actually find this curve? How do we find these solutions? We have to solve this optimization problem, or possibly its Lagrangian relaxation. That's very difficult to do, and it's something I'll talk more about. Until recently, until a few years ago, there's basically two different approaches to doing this that concern two special cases. The first special case is when x and y are finite values, have a finite set of outcomes. And in that case, we can just represent the conditional distribution of what I'll also maybe call the bottleneck variable t, so that's the intermediate representation. We can just represent the conditional distribution of t given x, and we can then optimize this function using some technique like Lahut-Uramoto is a common one. It's a technique used for rate distortion also. It's generally not a convex problem, so we can optimize it, we can find a solution, but it's not guaranteed to be the global optimal solution, even for the simple case. The other special case that's been considered is when x and y are continuous valued and jointly Gaussian. And perhaps not surprisingly, you can derive a closed form solution in this case. It's the IB curve depends on the eigendecomposition of this kind of product of a precision matrix and a conditional covariance matrix of x and y. And there's a very nice paper by Chichik in 2005 where they solved this. But beyond these two special cases, again, until recently, there hasn't been much progress. Okay, I'm just going to finish talking about introducing IB by mentioning some of the applications. So there's been quite a few applications in coding theory, source coding, and quantization, so finding optimal compression algorithms. There's a lot of not a lot, but there's some classic machine learning. They used it for things like clustering, topic modeling, some image recognition tasks. As I mentioned recently, there's been more attention to it in the machine learning community, and I'll discuss why that is. There's also been quite a few papers talking about using it for clustering, like clustering random variables or doing other kinds of information-theoretic clustering. And I think something, Greg, you worked on, at some point also, this kind of stuff. This is a nice paper from 2005. Talks about clustering using IB. There's also this really interesting line of research which asks, are real-world systems optimal in IB sense? So are natural systems, for example, or maybe neural networks, are they close to this boundary of having the best possible prediction given a certain level of compression? And there's at least two kind of important works in this line of research. One looks at the fly retina, and they basically measured the retinal activity of a fly that's shown different images. And they're very motivated by this idea, which is popular in neuroscience, called the predictive brain hypothesis, which basically argues that the fundamental function of the brain is to predict future signals given past signals. And what they looked at is they asked, if X is the past visual input that they show to the fly, and Y is the future visual input, both of them are distributed according to some kind of stationary statistics, and T is now the intermediate representation, which is just the neural activity of the retina. Is the neural activity of the retina close to being IB optimal? And this is kind of a representation of that information plane, and they argue that it is actually pretty close to being optimal. What does that mean? That means that essentially, it seems like the retina forgets everything about the past visual input that's not important for predicting the future. Right? This is the implication. And this was in PNAS in 2013. About 2 years ago now, I guess a year and a half, there's a really fascinating paper looking at color naming in different languages around the world, where they basically treated Y as some color, some maybe light frequency that we might want to represent using a word that we use to communicate to another person. And where T is basically, so, we can think of each language as cutting up the color space in different ways. And we can ask, are the languages that people use optimal in an information bottleneck sense? So it seems like they are actually quite optimal, much more optimal than would be predicted by a null model of words.
Do you know which language is the most complex in its color naming scheme?
I don't know. Do you?
Eskimos and a variety of flights.
I know Russian has some color words that English doesn't have, like a special word for light blue and things like that. I don't know. I suspect it might be like a Western industrialized country language where there's a lot of data. And
Russian.
It's Russian? That's the light blue dot?
Well, that's what we call it blue.
Yeah, exactly. Okay, so I talked about what is information bottleneck, what has it been used for. As I mentioned, there's recent machine learning connections, which I'll get to later. So the things that kind of we still have to talk about is how do we actually solve the information bottleneck optimization problem beyond these two special cases that I discussed. And a question that's been attracting a lot of attention, are neural networks optimal in an information bottleneck sense? And I'm going to talk about the first of these things first. How do we solve the information bottleneck optimization problem? And can we use gradient-based methods or neural network type methods to do so? So I'm going to put up here the IB Lagrangian, right? This is the Lagrangian relaxation of that constraint optimization problem, where we want to maximize the first mutual information term and minimize the second mutual information term. And this is a very hard problem to solve in general because there's all these intractable integrals involved that even to not just to optimize it, but even to evaluate this is very difficult. And the way we go about this is we're going to try to bound this objective with something tractable and differentiable that we can then basically optimize like a lower bound on the IB objective instead of this complicated to evaluate function itself. To do that, let me just discuss mapping between information bottleneck and neural networks. This is also kind of first developed by Tishby and some co-authors. So this is showing, which look basically, a schematic of a simple neural network with many layers. I'm going to this is going to indicate actually the input layer. These are going to be all the hidden layers, and finally we produce the predicted output. There's also the true output. So that's basically like the true label, let's say, that should be assigned to each input, which can of course differ from the predicted output. And it's important to notice that the true output is conditionally independent of all of the activity of the neural network, conditioned on the input, right? The true output is really just a function of the input. It's not a function of what the neural network is doing. So we can map it to the information bottleneck Markov structure, where the true output is y. It's the thing we actually want to predict. X is the input, the thing we have. And T, the intermediate representations, would be the activity of the hidden layers. And we actually can represent all of the distributions over these random variables in the following way. So the distribution over x and y is just given by the empirical joint distribution, for example, in the training data set or in the underlying generating distribution. And the conditional distribution of t given x would be some parameterized, maybe possibly stochastic map from input to hidden layers. T here can represent either a single hidden layer or a chunk of hidden layers or all of the hidden layers taken together. And finally, we can represent the mapping from the hidden layers to the predicted output using another parameterized conditional distribution. And I'm going to refer to the map from x to t as the encoder, and it's going to have parameters theta. And I'm going to refer to the map from t to y hat as the decoder, and it's going to have parameters phi. So this is kind of using naming from VAEs and so on. Okay, and we're going to look at how we might use this mapping to then optimize the IB Lagrangian with respect to basically now this parameterized problem. So we have these encoder and decoder parameters, phi and theta. And there's two reasons we might want to use neural networks to optimize this IB Lagrangian. The first one, because as I said, it's very tricky to actually solve the IB problem for general state spaces, and this could be one way to do it approximately. A different reason is we might think of this as being similar to neural network training, but we're now adding some kind of information-theoretic regularization. So we might be penalizing, for example, neural networks that don't have a compressed hidden layer representation. Again, please interrupt me if something is not clear. Is there any questions now? Okay. So how do we actually optimize IB Lagrangian? As I mentioned, we're going to look for a tractable and differentiable lower bound. Tractable, we can evaluate it quickly. Differentiable, we can optimize it using gradient descent. And we're going to look at the two terms in the IB Lagrangian separately, so the two mutual information terms. The first one is the mutual information between the true output and the hidden layer. We can break down the mutual information into this difference of an entropy and a conditional entropy. And here we use something called the variational upper bound on the conditional entropy. So we add to that entropy the Kullback-Leibler divergence between this is the decoding distribution that produces the predicted output given t, and this is the true Bayesian inverse of the encoding distribution, because this is the encoder, right? And it turns out that if we work through the math, this simplifies, and this actually gives us that upper bound is equal to the cross-entropy loss, which is the typical loss function that's optimized already during neural network training. So what that means is this h of y is just a constant that doesn't depend on our parameters. This is just entropy of the true output. We can ignore it. And what that means is we can lower bound the first term in the IB Lagrangian with minus the cross-entropy loss, which we know how to optimize very well, plus a constant that we don't care about. And okay, this is our little diagram. And remember I call this the encoder and the decoder. So one other way to think about what we're doing when we're minimizing the cross-entropy loss is that we're simultaneously increasing the mutual information between y and t, and we're trying to force the decoder to look like the Bayesian inverse of the encoder. And it's not necessarily, and typically it's not going to get exactly there, but it will try to get as close as possible. Right? And we're pushing it towards that because of this Hilbert-Leibler term. Okay, so what do we do with that second mutual information term? We now want to upper bound it, right? And there's basically two approaches that have been suggested in the literature, but actually I should say there's now three approaches because there's this kind of echo noise idea which could also be used for this, and I'm curious how well it would work. But as far as I know, it hasn't been run on the information bottleneck yet, which is the work of Greg and his group. But the two approaches I'm going to talk about, the first one has been called deep variational information bottleneck. It came out in ICLR in 2017, and it basically uses again this variational trick to upper bound to now upper bound the second mutual information term, and instead of using a variational distribution for the conditional entropy, it uses it for the marginal entropy of t. And essentially, what it does is it tries to push the marginal distribution of t close to some kind of variational distribution. And we can also think of it as a kind of regularization. It says, don't let the marginal distribution over the hidden layers deviate too far from some kind of desired distribution. Now, the variational distribution can be anything. So let me suggest is choosing like a standard unit normal, and in which case the math simplifies quite a bit, and our final objective function is just given by the cross-entropy loss plus like the norm of the hidden layer activity minus the conditional entropy of the encoder. And typically, the encoder distribution is just a deterministic function plus Gaussian noise. So this has a closed form expression, and this is very quick and easy to evaluate. And it's surprisingly simple. It really just penalizes the activity in the hidden layers. The other approach, which me and my collaborators proposed, and which has been around for a couple of years, but just came out in Entropy last year, begins by, again, we assume that the hidden layer map, the map from inputs to hidden layers, is represented by a deterministic function plus Gaussian noise. And we then use this previously published bound if the mapping from inputs to hidden layers is a deterministic function plus Gaussian noise, then the marginal distribution of the activity of the hidden layer will be a mixture of Gaussians. I hope that makes sense to everybody. And in some previous work, we published these lower and upper bounds on the entropy and the mutual information for a mixture of Gaussians. Right? And this upper bound on the mutual information is actually based on the distances, pairwise distances between the centers of the different Gaussians. So one way to think about it is, think of the input as a bunch of points that are then mapped by this deterministic function to the hidden layer space. We add a Gaussian to each point, and now we have a mixture of Gaussians. And now by looking at the distances between the different points, we can actually bound the mutual information that's flowing between the input and the hidden layer. Yes?
How tight is this bound? I mean, obviously sometimes it's equal, but in practice, is it close?
Sometimes. So in this paper, I should actually point you to the archive version because it fixes a couple of typos. We kind of explore this. We show it's very tight in many cases, and in other cases it's not tight. I'll show some results that it seems to be better than the variational IB. Yeah, it depends. It depends on how like clustered the Gaussians themselves are. When the Gaussians are, for example, like clustered, then it becomes exact.
Actually, I could have used this yesterday and doing my paper.
Oh yeah.
I was exactly bounding something like this.
Yeah.
Just to show that you can bound this and then it will bound whatever we need at the end.
Yeah.
But I was doing like this, so you have the centers of Gaussians.
Yes.
So I can kind of upper bound the variance of it.
Uh-huh.
And I know it's a zero mean, and then I say, oh, the highest entropy guy out of all these variances is Gaussian.
Yes.
And you get almost similar looking quantity, but there's no distance between the centers of Gaussians. So I believe it's like much worse one.
Yeah.
This might be.
Yeah.
Yeah.
Cool. Yeah, we can talk more about it. Right, and the distances here is measured by the exponential distance is measured by Kullback-Leibler divergence. We also show in this paper you can use many distance functions here, and some of them give you upper bounds and lower bounds. For example, if you use the Bhattacharya distance here, you get an lower bound. And so this leads to this, what we call the nonlinear IB objective function, which again is cross entropy loss plus this penalization for the mutual information. And you know, when we write it like this, it really looks like it's a kind of regularization term, right? We're adding some kind of information-theoretic regularization to cross entropy loss. In this paper that came out at the end of last year in Entropy, we show that, or was it this year? I forget. We show that we actually do better than a variational IB. So here I'm showing you curves. This is the information bottleneck. The recovered solutions when we optimize the blue with the nonlinear IB objective. The red is with the variational IB objective. And this dashed line is that achieved by just doing cross entropy maximization. And so this is MNIST. We do a little bit better, meaning like we get a little bit more prediction at the same level of compression. And this is actually a 2D PCA representation of the hidden layer activity when we train with these different objective functions. And we see both with VIB and nonlinear IB, the hidden layer activity is clustered. It has some clustering, but the clustering is much tighter with nonlinear IB. So it really forces, basically these clusters correspond to the output classes, and when we're so tightly clustered, we're losing, almost all information about the input besides just its class is removed. We also ran this on FashionNist. FashionNist is a recent plug-in replacement for MNIST. It's harder, so you see it doesn't come as close. This corner point is the best possible achievable, for reasons I won't go into right now. So we don't come as close to it, but you see we do quite a bit better. And again, we uncover more tightly clustered representations. The last result I want to talk about is this is so-called California housing prices data set. It's about 20,000 eight-dimensional vectors that are like different aspects of a house, and the prediction is just a number that's the selling price of the house. And again, we do better than the IB, meaning like we achieve more prediction at the same level of compression. But I think it's also interesting to see that we uncover quite a different intermediate representation. So we really uncover like a perfectly one-dimensional representation where the one dimension just represents the housing price. The color here is the housing price. So we've really like lost all information about the input except that one dimension of variation that we care about. And you see this is not the case for variational IB and mean squared error training. Yes?
Can we say that the overall the regularization acts like tries to put as much points close to each other as is possible by still predicting the task well? Was it
No.
analyzing the distance? Output?
No, it's not. I mean, it's much tricky. So like here, for example, it's trying to cluster the points. It's not trying to bring them all close together. For variational IB can be understood more in that way, that it's trying to bring the points close together, but still like being able to predict from them. But the nonlinear IB is doing something quite different. Because if the points are very far away from each other, they contribute almost nothing to the objective function.
Yeah, I was looking at the difference between second and third ones there. If you please go back. Yeah, you get like larger distances between clusters.
That might just be a scaling thing. Yeah.
Yeah.
Yeah. But I can tell you, like, e to the minus, it's like you have terms like e to the minus distance. So that doesn't contribute very much, actually. Okay. So, yes.
So I have a question. Did you also try other data sets that didn't work that well?
No, but you could probably find them. Yeah.
Okay. I
Yeah.
have a specific example. I was curious if you tried applying this method to, for example, CR10.
No, I didn't. That would be interesting. I will say, two things. First of all, while it achieves somewhat better performance, it is quite a bit more computationally costly. And that's because basically for variational IB, it's a very simple penalty that's basically like it has almost no additional computational cost. For nonlinear IB, we have to measure these pairwise distances between samples. So really our computational cost scales as like the size of the mini batch squared. And so that's a pretty significant increase. The other thing I'll mention is this is pretty low dimensional hidden layer, so I think it's like either 5 or 10 hidden layer neurons. I suspect this might not work very well for high dimensional hidden layers where distances become really not very meaningful in high dimensions. Yes.
I don't understand the figures here. I mean, it looks visually like in the bottom plots that there's a substantial difference with how nonlinear IB works, and it seems to be capturing or compressing the data a lot better. And yet, when I see the upper plots, the difference doesn't look that big. I mean, these are small fractions of bits.
Yeah.
How do I make sense of the fact that it seems to be much more clustered, but the difference doesn't seem to be very significant in the upper plot?
So maybe one reason, I mean, this is kind of hard to say what is significant, what is not significant, right? Especially with bits, which are, you can think of as like log units, right? Like a small log can be a big e to the log. But one thing to keep in mind is that there is noise. These are stochastic networks, so there's noise injected from the mapping between the input to the hidden layer. You actually need that for the mutual information between the hidden layer and the input to be non-infinite. And so even though, this looks like it might have a lot more information, I'm not plotting here like a Gaussian added to each point. So a Gaussian added to each point might actually make this a lot less information contentful, if that makes sense. Yeah. That would be my guess. Why they look quite different, but the performance is not so different. Yeah. Okay, before I continue, yes, yeah.
My next question was that this mutual information between x and m.
Yeah.
Are you plotting the upper bounds that you compute using
I'm plotting here like a Monte Carlo estimate. Does that make sense? So we actually get the representations using both methods. We can then Monte Carlo to estimate the mutual information, which is costly but more accurate. Mm-hmm.
On the last point about the representations being stochastic, if you go back to the first, so if your nonlinear IB is as well separated as it is, like, do you have a sense for whether the encoder is adding, like how much noise the encoder is adding? It seems like everything in the blue dot, all we need is the scale divergence. Small. and so that could happen.
I don't,
Very little noise.
yeah.
Yeah.
Right. I don't know. I should probably maybe plot the size of the noise. Yeah. Yeah. Right, but I mean, you're right that once it's actually a highly nonlinear objective function, which is I had trouble. Now it works pretty robustly, but I'm a bit surprised because it's if 2 points are very far apart, the gradient for bringing them closer, for example, or further away is very, very small. Yes.
I was just curious if there's a meaningful difference between like using cross entropy versus MSE in the sense that your first few plots you had like the cross entropy only it basically like caps the distortion for these, whereas in the last plot you're using MSE it exceeds the distortion.
Right, there's actually
MSE.
there's a generalization benefit. I mean, MSE is basically cross entropy for continuous valued things. So
I was just curious about the difference.
I think it's an artifact of the data set, or not, it's a property of the data set. So in general, like doing this regularization doesn't necessarily give you generalization benefit, doesn't necessarily improve performance. Alemi claimed that it did, but I could never replicate his results. Alemi actually proposed variational IB more for like adversarial robustness. He claimed that it gives you adversarial robustness, which I find believable. I don't know if that's true or not, but it doesn't necessarily like raise you above not penalizing. It turns out that for California housing in this architecture, it does, but Okay, so I just want to finish this little section by talking about a recent paper that we published in ICLR in 2019, which basically from doing this project and this estimator and stuff, we ran into some very surprising problems of actually performing information bottleneck on with neural networks on typical machine learning data sets that was kind of unacknowledged or maybe unknown. And to sum it up, the message is that when the thing you want to predict, when y is a deterministic function of the input x, a lot of very strange things happen, and in some ways, like information bottleneck kind of breaks down. And, in many supervised learning data sets, especially classification data sets, it's assumed that basically like each input has one true label. Of course, there's multi-class learning, there's exceptions to this, but I would say the standard assumption is that each input has one true label. And of course, in every sort of classification data set, that also holds in the sense that each input typically appears just once and it appears with just a single label. So the empirical distribution also makes y be a deterministic function of x. What happens when y is a deterministic function of x? In that case, it's not too difficult to show that the information bottleneck curve actually looks like this. It has this piecewise linear shape, so it's no longer strictly concave. And this leads to several problems. So this corner point is just the intermediate representation that's equal to y, which is equal to f of x. So there's several problems. I'll talk about the two major ones. One is a kind of practical problem, and one is a more conceptual problem. So the practical problem is that when the IB curve is not strictly concave, when it has this piecewise linear shape, that there's no longer an equivalence between the constrained optimization problem that defines the IB function and the Lagrangian relaxation, which is this thing. If it's strictly concave, we will find the same solutions by either solving this or by solving this. But when it's piecewise linear, which again is the standard situation in machine learning, that's no longer the case. And we can understand that by sort of thinking about the geometry of optimizing the IB Lagrangian. So optimizing the IB Lagrangian is like looking for a line in the information plane that has slope beta and looking at where that intersects the curve. Now, if it's strictly concave and we vary beta, we're going to intersect the curve at different points and we'll uncover different solutions. If it's not strictly concave, then basically for all values of beta, we're just going to hit that corner point and we're going to find the same exact solution even while varying beta. And it's just some simple math can be used to show that this T star, which is the corner point, is optimal for all beta. And many times we want to explore this trade-off between compression and prediction, and we can't do it by solving the IB Lagrangian. So we actually proposed what was to us a pretty surprisingly simple solution, which is if you just square the compression penalty, so instead of optimizing the mutual information minus beta times compression, you optimize the prediction minus beta times compression squared. You change the geometry, so you're now not looking for these iso lines, but you start looking for these iso curves. And you can then explore even a piecewise linear curve effectively and find different solutions while varying beta. And we showed this, I think this is MNIST, and we just show that if we run our nonlinear IB method and we optimize the regular IB Lagrangian, then we essentially, for most values of beta, we jump from either the trivial solution at the bottom, which collapses all inputs to a single point and has no, maximal compression, no prediction, and then we jump from that to the full solution, which basically gives us 10 clusters. But if we optimize the squared IB Lagrangian and we vary beta, we basically hit different points on the curve. And so this was actually a major stumbling block to getting nonlinear IB to work. I couldn't figure out why it was sort of not finding these points. And so the results I showed earlier are all when optimizing the squared IB functional. Variational IB still seems to work even without this squaring trick. It actually works whether you square it or not. And I think that's just because variational IB does a much harsher approximation that sort of puts in a certain kind of prior. So it's optimizing something quite different in a way than the true IB Lagrangian. Any questions about this part? Yeah.
So you said this is the case. Okay, y is a deterministic function of x.
Yeah.
You have a labeler, and it's for every x is exactly one label.
Yeah.
No label noise. So then we get this line that connects the two solutions, the sort of zero information one and the best one. And I think I remember you saying something like that before. That's kind of like I'm wondering whether there's more than one way to do that spectrum. It sounds like there's a trivial one where you could just add noise progressively.
Let me get to that. This is my next slide. So this is all the practical problem, which can be solved, for example, just by squaring the compression penalty. We also pointed out that there's a kind of conceptual problem, and it's the following. So we usually think of this IB curve as being full of really interesting representations of the input. So they're optimal in the sense that they throw out everything not necessary to predict the output and capture just those features which are good for predicting the output. And so they should give us really interesting representations of the input. And they should uncover useful features, right? At least that's kind of the intuition and that surrounds that solutions on the IB curve. And, coupled to that is the fact that typically these solutions on the IB curve are really, really difficult or maybe even impossible to find. We can approximate them, but we have to do a lot of optimization. When we have this property that y is a deterministic function of x, none of this holds, meaning that, first of all, we can uncover the whole information bottleneck curve in closed form, and we can do it by families of solutions such as the following one. So each point on this increasing part of the curve can be generated by the following family of solutions. Just output t equals y, so t equals f of x, which is that corner point, with some probability alpha, and output is 0 with some probability 1 minus alpha. As we vary alpha, we'll cover different points and will be IB optimal. And okay, I mean, that's even nice that we can uncover the whole IB curve in closed form, but like these do not look like any kind of interesting representations of the input. They're just they're in a sense, like with some probability, they're outputting a completely sort of uncompressed version, and with another probability, they're outputting something worthless.
Yeah, I kind of suspect that this might be the case for the non-deterministic case too.
Uh-huh.
I imagine that if y given x is some entropy,
yeah,
you can represent it as a function x and some noise, y to be a deterministic function of x.
Yes.
Some noise. Is there a decomposition like that? I believe there is. You can take any conditional distribution and represent as input on some independent noise.
Yes.
And that's the output gives you the y. And now I can kind of have this t to have this kind of formula where I sample the noise there, the label noise kind of y given x noise, along with alpha.
I'm not sure. I mean, really, things do. I don't have time to go too deep into it, but things do really change when it's a deterministic function. I'm not sure. I mean, you can certainly do that, but I'm not sure you can guarantee you would still be IB optimal.
So in some sense, it would be like you find whatever you can extract from x,
yeah,
like y hat or y star.
Yeah.
Even when things are stochastic, there's like y star has the most information you can get.
Yeah.
And then you throw information from y star using this technique.
Yeah, but you wouldn't stay I think you would just cover a line that way.
Yeah.
And if the curve is strictly concave, you're like deviating away from the optimality.
Yes.
You wouldn't stay on the curve. But it's something we should talk about. It would be interesting.
If the curve is concave, it means every new bit I cannot get like the super modular increases in predictions, right? As I
yeah.
go, right? So it seems if I achieve increase that is a line with slope 1, that should be good enough. Or no, it can be kind of concave but with kind of slope bigger than 1.
Let me go on, okay, because I have like 9 minutes to finish my talk. But we should talk about it. It'd be interesting. The point I'm trying to make here is that oftentimes people think of IB curve as being, and especially in recently neural networks, being IB optimal is some kind of like really special thing that means you have a good intermediate representation. And this shows like this is clearly not the case. I would argue, at least. Okay. The last part I want to talk about is the connection between information bottleneck and deep learning. And I should finish at noon, right?
Oh, yeah, that's good, yeah.
Okay. And I'll mention just 3 different things. First, can information bottleneck explain why deep neural networks generalize so well? The second thing I'll talk about, which I kind of mentioned, is can information bottleneck quantify the optimality of hidden layer representations? Is it good to be IB optimal for hidden layers? And the last question is, can information bottleneck be used to derive the kinds of things that we classically care about in statistical learning theory, which is like how well can we generalize? So the first part, can IB explain why neural networks work so well? Some of you have probably heard of this paper by Schwartz-Ziv and Tishby, where they argued, so Tishby is one of the inventors of information bottleneck, and they argued that like information bottleneck actually explains a lot of the mysteries or surprises about deep nets working so well. And they made 3 different claims. The first one, they argued that stochastic gradient descent dynamics, SGD, implicitly actually favors intermediate representations that are compressed. So neural networks trained with SGD end up having low mutual information between input and hidden layer, subject to having good performance prediction. And this is kind of explained with this information diagram, where you see during training, the hidden layers are increasing their prediction, but then they also start moving left and they start compressing. The second claim they made is that this compression, so having a low mutual information between input and hidden layers, leads to good generalization. And the last claim, which for interest of time I'll probably not talk about too much, is they argued that the different layers of a deep neural network will basically fall along different points of the information bottleneck curve, and in this way, like, explore the curve. So I was involved in a paper with Andrew Sachs and many other co-authors, where because we had this estimator of mutual information, and I was very interested in this paper when it came out, and we basically tried to replicate their results, and we couldn't. And so we published this kind of rebuttal. And I will say that, like, this paper got very big. It got written up in Quanta, Tishby's paper. It got a lot of attention, and I think it really, like, psychologically feels right, in the sense that we think of, like, oh yeah, generalization is about, like, not overfitting. It's about forgetting, like, the noise and remembering the concept. It should relate to compression and all of these things. So intuitively, like, it seems right, and but in practice, like, it just doesn't work. And I think the general idea that generalization has to do with compression and forgetting irrelevant things is not wrong per se, but, like, the mutual information between input and hidden layer is probably not the right way to quantify that. So I don't want to say, like, that the high-level notion is wrong, but it's information bottleneck doesn't really explain it. I'm going to quickly go over these claims. So the first claim is that SGD favors good compression, so low mutual information between input and hidden layer. And this is basically an artifact of how Tishby and Schwartz-Ziff estimated the mutual information. They basically took their hidden layer activities recorded while operating their neural network, and they binned it, and then they built up histograms and calculated mutual information using that. The problem is, the most fundamental problem, and I think the root, the deepest problem with Tishby's paper, is that when you have a deterministic neural network, meaning there's no noise injected in the mapping from input to hidden layer, which is the kind of neural networks that, are typically considered in machine learning, the mutual information between input and hidden layer is infinite. So we have basically a non-noisy mapping from continuous valued random variables generically that's going to have infinite mutual information. So, and, like, you can just show that mathematically. So if you're getting finite mutual information, that has to be some kind of artifact of your estimation scheme or your assumptions, and that's saying more about your estimation scheme than about the actual underlying mathematical object. I don't know if that's clear or not, but here they used there's a deterministic neural network, but they did this binning, and if you basically bin a saturating nonlinearity, such as the one they used tanh, then, as the network trains, it's true that the weights tend to get bigger and bigger, and it tends to push the activity towards the edges of the range of the nonlinear function. And if you bin it, you will see mutual information going down over time, because the entropy goes down over time as the activity is concentrated in just 2 bins, or 1 bin. If you use a rectified linear unit, for example, then you won't see this. And again, I want to emphasize that it's also not the case that, like, tanh really is compressing, but ReLU is not. It's like the interplay between the nonlinearity and this choice to use a binning estimator, which is far from clear is the right. It's not even clear what you're estimating, because we know the true mutual information is infinite. So, anyway, the point is, if we just do rerun their binning estimator, and we can recover these results where tanh seems to compress at the end of training, but rectified linear units do not seem to compress. But both of this is kind of like, again, like, the true mutual information is infinite. So really, to talk about information bottleneck in neural networks, you have to be injecting some noise into that mapping. The other claim they made is that compression, again, as they measured it, helps generalization performance. This is very easy to refute. Just by running things, we saw that rectified linear units do not compress in the way that they measured it, but they achieve basically the same generalization performance. And so you can either have, binned compression and bad generalization, binned compression, good generalization, or no binned compression, bad generalization, no binned compression, good generalization. So they're totally orthogonal. And I'm going to skip this, but in general, there's no reason to expect with that having high compression will lead to good generalization. Tishby often claims that he has a proof that it does lead to that, but the proof is based on like completely absurd assumptions, which I can talk about afterwards, and it's completely irrelevant to any actual machine learning. For interest of time, I'm going to skip this. Basically, in that caveats paper, we showed that if y is a deterministic function of x, you cannot have, your different layers can't explore this trade-off curve. It's just impossible. And it's actually also interesting. This is a paper from Tishby's paper. This is a figure from Tishby's paper. It's interesting to look at the axes here. 985. So it's a kind of artifact of zooming into like an extreme corner of the curve. But anyway, yeah, I'll have to go kind of quick. So there's recently been a big field of so-called representation learning. I heard there's even a course offered at USC on the topic by Greg. And this is kind of a new field that's tries to ask, what are good qualities of hidden layer representations or intermediate representations uncovered by machine learning architectures? Beyond just giving good prediction performance, maybe we want something like that's really interpretable, or we want it to be invariant to certain transformations, or we want it to be disentangled. So, for example, if we're learning faces, we might want the age to be disentangled from the ethnicity or something like this, right, of the face. And we might want it to have some kind of smoothness or formal properties and so on. And one thing that people often bring up, which is not unrelated to the other ones, is that we want these representations to be minimal, or we want them to be compressed, meaning that they don't capture extra information about the input that's not necessary for the task they're trying to achieve. And one might ask, okay, well, is being information bottleneck optimal, so having maximal prediction at a given level of compression or maximum prediction at a given level of prediction, is that a good thing for intermediate representations to have? And I talked already a bit about this, where I said that, I actually don't think so. Maybe it's a necessary, but it's not a sufficient condition. But we also showed that even if, for example, the hidden layer representation is just a clustering of the inputs. So you saw some of these plots, for example, for MNIST, where the hidden layer representation is just like each input class, the inputs corresponding to each class, are packed into its small cluster. We can then increase compression at the cost of prediction by merging clusters together. But it's easy to show. And this will explore, actually, this will explore the information bottleneck curve, and it will do that without just injecting noise. We can show that this kind of compression is like totally insensitive to any of the semantics of the clusters, which of course makes sense because we don't know about them. But if we had two classes, like two different types of dogs and two different types of champagne glasses, and we collapse those clusters together in order to achieve more compression, that's just as good as collapsing like this wine glass with this dog breed and this wine glass with this dog breed. So again, it suggests that like being IB optimal is not really something to brag about, I would argue. Or it's not in itself. Maybe it is necessary, but again, it's definitely not sufficient to be what we might think of as a good representation. This, luckily, is my last slide, and I'm just going to briefly talk about the question of can IB be connected to things like generalization bound. The generalization bound bounds basically the difference between the error that we incur on the training data set, which we minimize, and which is often can be made very small, and the error that's incurred on held out data. There's recent work that reformulates the relationship between information bottleneck and machine learning. And instead of thinking about the compression in terms of the mutual information between the input and the hidden layer, it actually thinks of compression in terms of the mutual information between data set and the parameters spit out by a machine learning algorithm when run on that data set. So we think of like a machine learning algorithm as a kind of communication channel that takes as inputs data sets and spits out parameters that are fit to those data sets. And instead of looking at this usual compression term, so the mutual information in X and T, we look at the mutual information between data sets and parameters. And this is very hard to estimate, but it actually turns out to be much more closely related to generalization performance than this, which for a variety of reasons, if you think about it, makes a lot of sense. And several people have derived bounds of this form where basically the generalization error is bounded by like the square root of this mutual information divided by number of samples, which is oftentimes a much better bound than traditional like VC dimension type bounds. Okay, so that's it. These are some of the collaborators that I worked on this stuff. So thank you.
Awesome. Yeah, we got some questions in, but let's do one or two quick questions.
Yeah. Why we play with mutual information in all this stuff rather than some other notion of dependence or dependence?
That's a good question. I mean, that's not an easy question to. I mean, so mutual information, has a very important operationalization in information theory, in terms of the capacity of a channel, and that's similar to how it's also operationalized or related to how it's operational rate distortion. The mutual information arises very naturally in rate distortion theory. And that's a big part of why it's also used in information bottleneck, because information bottleneck is motivated by rate distortion. Now, in the original paper, Bialik and Tishby and Pereira, they tried to give a kind of operationalization of IB in a kind of like coding theory type way, and it sort of works, but.
Yeah, because at the end, what do we want the bottleneck? Like good performance, predicting performance, like good weather predictions with minimal transfer to data centers, right? That's what we want.
That's sometimes.
Maybe you'll get that with other notion of dependence or.
Which mutual?
Like it's easier to play theoretically with mutual information, has nice connection. But at the end, it experiences all these weird behaviors. Like you can cluster dogs, champagne cups together. It would count it as a fair compression, whereas that's like probably is not a smooth compression.
Yes, but I don't think you would fix that by just using a different distance measure.
Something, for example, that has kind of embedded in it.
Like
maybe
Wasserstein or something like that.
Yeah, that's like counts as a first example. Something like that might kind of trim down these cases, but live behind these motivations and nice connections to different coding theory.
I mean, you can put in a distortion function too. Right, like I actually had like typically you would put in a distortion function. That's the more classic approach, like something like perceptual error.
Yeah, or let's say, let's speak practically. If we care about bits, when we say that's an amount of information is stored. In reality, the stochastic variables, when you flip a coin and either you take 0 or the entire thing, like how would you really represent that you are transferring? Why don't we put like I want 1 gigabyte of data? This is my compression. I don't know what you do there. Achieve me good things there. and then maybe you don't have this coin flip situations because that you cannot. No, sorry.
There is a deterministic. Really just treats that. That's like a more like what you're saying. It's like a given capacity. Now let's do.
Yeah, but we show in the paper, we also analyze deterministic information bottleneck, and we show it has all the same problems basically. So like, okay, instead of just adding noise, you can just like cluster things in any way, and then
All right, so we've gone a bit over, so let's thank Artemy again, and he's around if you want to.